Right. Let's start the discussion of ripple tank experiments. Right. First, we should identify the component of ripple tank. At here, horizontally, we have vibrating rod, right? Now you have the tuner, right? Here, vibrating generator, that's the motor. This one is vibrating rod, which is connected to the vibrator or vibrating generator, right? And here we have tree. This one is the tree or ripple tank, right? This one is the ripple tank. It consists with this kind of metal mesh. Here we have metal mesh available to avoid the reflection of the incident waves generated from the vibrator, right, Pudha? Okay. To avoid reflection, we are using wire mesh. Can you label wire mesh on your tube, Pudha? Here, this one is wire mesh. This is the observation area, right? Here we have observation area. By placing white paper at the bottom, we have to adjust the height of ripple tank to clearly show the images on the observation area, right? Okay. Then it seems at the observation area, it seems this kind of bright regions, and in between these two bright regions, we have dark region. These are bright regions, right? Done. That is called the observation area. And on the water surface, due to the vibration of the rod, this kind of transverse waves generated like this, no? As the monochromatic light source light at here, it emits the light rays. They're traveling through the crest as well. Troughs, then through the crest, bright regions are occurred, and through the trough, dark regions are occurred. Right to the clear. That is the process of formation of wavefronts by using the ripple tank. After achieve that wavefronts by seeing the variation of wavefronts with the different kind of applications, we are going to discuss about demonstration of reflection, refraction, diffraction, and interference. Under the ripple tank, basically, primary thing in the 16th and 15th century, to demonstrate the reflection, the best way is this one, right? After completing the ripple tank experiment, they have identified some special incidences in physics can be demonstrated by considering the wavical nature of the wave. And some incidences can be demonstrated by considering the ray property of the wave. Then we are assuming for the demonstration of reflection and refraction, wave as a ray. For the demonstration of refraction, diffraction and interference, we are using, yes, wavical property. Without considering wave nature of a wave, we can't demonstrate spread of the wave, diffraction, overlap of the waves, interference. And without considering the straight line motion of the light wave, like light rays, then we can demonstrate the wave reflection and diffraction. Okay, that's it. Right, let's start. Question number 166. Explain how you would demonstrate the bright and dark regions of the observation area of the ripple tank. How would you obtain the bright and dark regions? Then can we draw a simple diagram right here? The function is on the water surface. If you consider this one is the water surface, if this is the water surface, here we can identify this kind of transverse wave nature due to the vibration of the vibrator, rod vibrator. Then some light rays that are hitting on the crest like this and trough like this. Here again crest like this and trough like this right here. And then they are converging. At a point. Here these are diverging as the concave shape of the water surface. Here converging. Here diverging. Here converging as the crest. Then you can say this region makes this kind of bright region right here. This is the rough diagram that can be drawn to indicate the formation of bright regions and dark regions by using the ray diagram. Okay, can we copy this one first? And here to here gap is wavelength, right? That's it. Okay, now after copying the diagram, we have to draw how do we obtain wave, bright region and dark region in the ripple tank. Okay. Copy the diagram. Okay, can you write the explanation? Yeah. After formation of after formation of transverse waves on the water surface on the water surface then crests are forming the converging process. The crests are forming converging process of the incident light rays on the crest. Incident light rays, that's enough, right? Then bright regions are resulted. But the light rays that are fallen on the trough are diverge then dark region is resulted. Then the dark regions are resulted. Therefore, bright regions are separated by the dark region. By the dark regions, right? Okay. That's enough. Next one. 167. Explain how you would demonstrate the wave reflection by using ripple tank. Can we consider that? Explain how you would demonstrate the wave reflection by using ripple tank. Right. We can copy this kind of diagram now. Here we have if this one is the ripple tank while observing through the upper view, right, top view. This one is the rod vibrator. Let it, this one. This is the rod vibrator. This one is vibrator. This is the rod vibrator. Then it produces wave fronts, right, that are traveling towards right side. We can say wave fronts are traveling towards right side as the formation of wave fronts by the vibrator. Then we are going to keep a barrier like this. It's an inclined barrier. Inclined barrier is placed right here. We have this kind of barrier, right? Okay, then wavefronts are operated from here. Then we can see this kind of wavefronts are traveling until hits with the inclined surface, right, Buddha? Okay. Then after they have hit with the surface, we can see it's like this, Buddha. This one is the path of the incident beam of light, broken line. And here we have normal, and they are reflected like this. This should be the reflected part. Basic theory, this angle I should be equal to this one. Incident angle equal to reflected angle. Then wavefronts are reflected from that surface like this by keeping perpendicular to then wavefronts are coming like this by keeping perpendicular condition right here, and incident light beam, incident wave beam is also perpendicular to each other. Here we have incident one. This is incident one. Here we have reflected wave. Right, Buddha? Okay, that. This is the way of formation of wave reflection, right? Can we draw this one and note down? This is obstruction. Okay. Okay, write the explanation. Keep an obstruction inclinedly on the Ripple tank. Keep an obstruction inclinedly on the Ripple tank. And generate the straight wavefronts. Generate the straight wavefronts generate the straight wavefronts and observe the way of the reflected wavefronts, after hitting on the incline obstruction. The Ronne property, first thing, wavelength of incident and reflection getting same. This one wavelength, this is also wavelength, right? Wavelength same. Okay, question 168. Explain how would you demonstrate the wave refraction by using the ripple tank. First of all, you should know this one. If this is the ripple tank, here we have water surface. Generated waves should be arranged like this. For the basic investigation of especially refraction, this amplitude of the wave should be negligibly small, which means the almost depth of the water surface, if this is h, that won't be changed with the motion of the wave. As the wave is generated on the water surface, you can see this is having the amplitude. If this amplitude is a considerable one, this depth from the water surface changes in between crest to trough. Clear with that? Okay, to maintain the constant average height, we are going to manage the amplitude of the wave negligibly small, right? This amplitude should be a negligibly small one. Amplitude S OE, let it take. Let this value A, amplitude. Then wave velocity of the transverse wave on the water surface. Wave velocity V on the transverse wave on the water surface is written by using V equal to GH. This is the standard equation of waves generated on the ripple tank. First of all, can you manage this one? Write down speed of the transverse wave, on the water surface. Speed of the transverse waves on the water surface is written as, right? Can you copy the equation and the diagram first? Okay, then demonstration of wave refraction, right? To achieve this, we are using this kind of ripple tank with the different heights. We can keep here this kind of glass block. We can keep here this kind of glass block to change the height of the water surface like this. Then we can change the height of the water surface like this. Then the function is at this side wavelength decreases, at here wavelength increases. Okay, can we copy this kind of diagram first? Right, this kind of different height of the water surface should be obtained. This is the water surface, right? And then wave is generated with the small amplitude, then like this. Wave fronts generated like this, and the amplitude of the wave slightly change, but especially wavelength changes, right? Yes, from here at this region, wavelength changes. Then can you note down? This one is the height. Let it h1. And the height of the water surface is h2. When the light rays are fallen on this one, on the observation region, if this is the observation region, it shows this kind of formation of the wave fronts, right? How? And this one is the blocking area like this. If this is the glass, if this one is the glass block, right? Then here we have wave fronts arrangement, blue color. Here wave fronts are closing like this. At the glass region, wave fronts are closing, but these two outside, no? Here deep region, here deep region, at here only shallow region, at here deep region, right? Then the wave fronts arrange like this at this region. Right, the corresponding line of this one lied right here, like this. Okay, clear. That's the variation of wavelength. At this region, we can see here, deep region, this is like rare medium. This region, shallow region, wave speed decreases, V directly proportional to h, root h. This region is deep region, then velocity v1. At here, velocity v1 larger than this one. Velocity decreases, no? v1 larger than v2. Then this region seems rarer medium. This region seems denser medium. What is the reason of denser? Speed decreases. Here, what is the reason of rare? Speed increases. Then transverse wave, it's same as light waves, right? Light having the rarer medium, fastest velocity. Light is having the least velocity in the denser medium. Then rare and denser mediums are separate, like that, no? Then we can demonstrate the wave diffraction. I think it's better to copy these two too, right? Okay. Let's take. In the given space, we have to manage, right? Okay. Okay. Can we continue question number 169, 170? And here we have glass block. kept inside the ripple tank water surface, no? Incident wavefronts going like this. You are asked to draw the arrangement of wavefronts, right? Can we copy now? Like this. The drawing one, we can arrange another color. At here glass block, then this could be this one rare medium, that one denser medium, right? Okay, then wavefronts are closing. The full area does have the glass block, no? Like this. After passes that location, again it enters to the same division. Same, this and that same, right? Then same wavefronts resulted. Can you manage it on the diagram? And here wavelength, let it lambda 1. Here same as lambda 1. Here lambda 2. Lambda 2 smaller than lambda 1. Copy? Right. Next one, this one. Wavefronts. Here, closing, no? They are closing right here. And wavefronts are coming like this now. This is the path of incident of the wavefronts. And then here we have normal. Put the normal. This is the normal. And then here we have denser medium. Here this one is this one rarer medium, this one denser, and it goes to again rarer medium. No? Yes. Rarer medium, then the transverse wave should be bent. Speed is high, no? Away from the normal, like this. This could be the path of the refracted light ray. Refracted transverse ray, no? Transverse wave. So you can say this angle is angle of incident. This is I. This one is R, right? Done. Okay. Then can we arrange the path of the bright lines? And then we have to copy them like this, no? Like this. Right here. The wavefronts going like this, they are bending right here. Like this, no? Right. Then can we name this here? This one, deep region. This one, shallow. This one again deep. Then here we have denser medium, rarer medium. No. Here we have denser medium. Done. Right. Can we complete? Let's see the next page. Okay, 171. You are asked to draw again the same question, no? Basic process of 169, 170. Again, we are going to demonstrate way of refraction, right? Okay, here we have inclined glass block like that. Okay, can we complete now? Right here. Right. Is that clear, brother? First, we have to look what is deep region, what is shallow region. And after that, we should identify then deep region is the fastest speed region, then like rare medium. Shallow region is the slowest area, then slowest area is dense area, then the direction of the incident path of the light ray should be bent towards the normal from denser to rare, moving away, bending away like this. No? Here, angle of incident here, angle of refraction, large angle. Right, done. Okay. Right, can we check 172 now? Always we have to draw the wave fronts perpendicular to the wave fronts perpendicular to path of the direction, right? Like this. Okay, clear. 172. Explain how you would demonstrate the wave diffraction by using ripple tank. Wave diffraction. First of all, can you define what is diffraction? What is diffraction? Spread of the waves when they are traveling through an obstruction with the whole spread. නේද හැම පැත්තටම විහිදෙනවට අපි කියනවා diffraction යටින් ලියලා. Can we write that here? On here. Spread of the waves into all the directions. Spread of the waves into all the directions when they're traveling. When they're traveling. When they're traveling through an obstruction with the holes. When they're traveling with the holes. That right? Okay. Explain how you would demonstrate the wave diffraction by using ripple tank. Right. Okay. Can we copy the diagram like this? Demonstration of the diffraction. Keeping an obstruction with the holes, no? Obstruction like this. This kind of hole with the obstruction. And this kind of wavefronts going like this. When they hit with the obstruction with the holes and the corresponding wavefronts will be spread throughout the entire direction like this without changing any kind of wave property. Then under the wave diffraction, there is no change of any kind of property of the wave. Here we have path of the incident, and after they have traveled through the obstruction with the hole, they spread into all the directions like this. Right here. They spread into all the directions. Got it? That is the diffraction as well. Can you manage this? 2. Here we have wavelength, and here we have also wavelength. Done. Right. To check the arrangement of all the abilities of wave diffraction, you are asked to identify completing the wave fronts related to the wave diffraction, and 3 diagrams are mentioned. No? Okay, after copying that one, can we enter to the next one? Right here. First one, complete the wavefronts related to the wave diffraction, obstruction with the small hole. And here, can we underline that one? Obstruction with the small hole here. And here, large hole. So, can we complete now? Here we have obstruction. It's a small hole, no? Then diffraction becomes sharp. Here, diffraction sharper. like this. Okay, then here we have large hole. Relatively that large hole, no? That's a large hole. Then diffraction is poor. Poor diffraction result. Let it like this. Diffraction is poor. Spread is not sharp, right? That is called weak diffraction. This one called sharp diffraction, like this. Here, diffraction sharp. Here, diffraction weak. Pathirima adui, spread is poor, like this. Initially traveling direction, only this direction. Initially, only this direction. Wave goes only into one side. After traveling through the hole, they spread throughout the entire volume. Clear with that? Okay, right. Third diagram, 175. Can we complete now? Okay, 175, 76. Related with the same function, no? Can we see both together? Okay, here, obstruction with a hole, same size as 175. These two holes are same size, but here with a wavelength lambda 1, here wavelength lambda 2, lambda 1 is larger one. Lambda 1 larger, then we can say this one having large wavelength having low frequency. Here, you can say lambda 1 is high, then frequency is low. Here we have low pitch sound, no? Low pitch sound. Okay, then for the low pitch sound, diffraction becomes sharp. You should memorize this. Then transmission of the wavefronts into all the directions, right here. And here, same hole, but wavelength is, let's see here, wavelength is small, no? Lambda 2 small. Then frequency is high. This is called high pitch. High pitch sound is having poor diffraction. Poor diffraction, like this. Spread is poor. Spread is low, right here. Compared with that one. Okay, then we have to write and we have to study with the correct configuration. මේවා විභාගවලට අඳින්න ඇවිල්ලා නැහැ. Last exam question only for the ripple tank is 1998. හරි. මෑත ඉතිහාසය වැඩිපුර ටච් කරන ස්කූල්ස් වලදී අපිට හුඟක් වෙලාවට මේ ඩිමොන්ස්ට්‍රේෂන් එක හම්බ වෙන්නේ නැහැ පුතා. Classes හුඟක් තැන්වලදී අපිට ripple tank කියලා කියන්නේ just MCQ question or avoiding one. But පුතා, care should be taken. It may have structured essay sometime, right? Okay. After copying this one, let's start next. That's enough, right? Okay. From 177. Let's consider 177. The small obstruction is at the middle of the ripple tank. Here wave fronts are coming. No? Wave fronts are coming like this. And they are hitting. Here wave fronts are hitting on the small obstruction placed at the middle of the ripple tank. Then after collision of the wave fronts with this one, wave fronts will be spread by preparing the circular wave fronts like this. Then spread of the waves into all the directions. Here, wave spread is made into all the directions. After hitting on the small obstruction, they're traveling like this now, into all the directions. Okay, can we copy this one? Okay, this incident is called irradiation. Irradiation. Spread of the waves into all the directions after they have hit with the small obstruction. Small obstruction, that is irradiation. Irradiation, right? Irradiation, anything, right? Okay, 178. Explain how you would demonstrate the wave interference by using the ripple tank, right? To achieve this, Dharwani, we need two rotating motors, right? We need two rotating motors like this. Two rotating motors are needed. One is demonstrating, one is switched and placing on the water surface to demonstrate this kind of circular wave fronts. Other one is also switching and placing on the water surface to demonstrate, to generate this kind of circular wave fronts. See the arrangement like this. Wave fronts will be traveled right here. Then, okay, those dark lines, those lines, these lines represents crest. And this black line and purple line both are represented crest. When the crest are meeting like this, here we have a crest, here we have a crest. When they are meeting, when they're traveling into opposite direction, the amplitude of the crest increases, then sharpness of these points, this, the situation when they are intercepting with each other will have a sharpness. We can see these regions are relatively having high brightness. That's it. And අපි name කරනවා sharp. Sharp regions. And here, in between, මෙන්න මෙයාගේ brightness පොඩ්ඩක් අඩු වෙනවා. What do you call that? That is this region here, this one, this area. මෙන්න මේ හරිය brightness පොඩ්ඩක් අඩු වෙනවා. That is light in between two crests. No, two crests means trough location. Trough and crest. Trough like this, crest right here. When they are overlap, we don't see the wave if they are having same amplitude. This amplitude and this amplitude getting same, the amplitude becomes 0. That's it. Okay. Then note down here sharp regions. Here, low bright region. Low bright region. Okay, next. How would you explain the constructive interference by using a string? How would you obtain or how would you explain constructive interference by using a string? Right. We can show like this. No? Here we have stretch string. Here we have stretch string. This is having the amplitude A1. Here we have same wave pulse or another wave pulse with the amplitude A2. This one is vibrated by using this kind of vibrator. This is also generated by using this kind of oscillation. Right, like this. This one traveling towards right side, this one traveling towards left side. Clear? When they are meeting, at a point they are meeting, then amplitude increases, then this one becomes A1 plus A2. That is called constructive interference. After completing the interference, they are separated like this. After completing, this one is A2. It goes like this. This is A1. It goes like this. They're separated after completing the interference. So this is before the interference. Before the interference. Here at the interference. and this one is after the inference. Okay, under the question number 179, can you copy this diagram? And same as that, can you copy 180? Okay, 180 and 181, can you complete now within 2 or 3 minutes? Okay, next one. How would you explain the destructive interference by using the string like this? Destructive interference. It is possible to take like this. Here we have crest, and here we have trough with the amplitude of A1, with the amplitude of here A2. They are going into opposite direction. Then, first thing, when S1 greater than S2, we can see this kind of wave pulse at the destructive interference of A1 minus A2. And here we have when S1 smaller than S2, then we can see this kind of one. But this one, half of the wavelength, no? Half of the wavelength. To demonstrate the constructive or destructive interference, wavelength should be same, no? Wave property is same, amplitude only different, energy only different one. Different one is energy. One is having high energy, the other one is having low energy. That is the difference, right? If they have different kind of wavelength, even though they are overlapped, that is not worth to hear or making the constructive or destructive interference. Then wavelength should be same, right? Okay. Wave properties should be same. Okay. Then here same process, wavelength lambda by 2, and here also lambda by 2, but amplitude A2 minus A1. As well, when S1 equals to S2, you don't see any kind of wave pulse. This is you can see only the string at the situation where the wave pulses overlapping with each other. And then after completing the overlap, you can see the wave pulses, they are going like this. They have traveled like this. This one, amplitude is, it's A2, and here A1. Done. Okay, can we copy? And the boy hari වැරදි දාගන්න. අනිත් අය බාන්න complete කරා. Right, 181. Okay. What are the main types of wave reflections? Main types of wave reflection. Right then, first, inverted reflection. Second one, non-inverted reflection. Inverting reflection first. Second, non-inverting reflection. Inverting reflection and non-inverting reflection. Inverting and non-inverting reflections. Next one, complete the following wave diagrams which are created on a string or strings. Okay, first string, wave pulse is traveling towards the rigid obstruction. What will happen then when it is reflected? Can you copy quick as possible? Okay, this is rigid boundary. Then the wave pulse will be reflected like this now. Here, rigid boundary, then wave pulse is completely changing its pace like this. It goes like this. Reflected wave. This one is the front one. If this is X, this should also be X. X is the frontward one. 182. Then 183. This is a ring. Can you note down this one? It's a light ring. It is movable one. It's movable here and there. Then wavefront is transmitted like this, no? Right here. Reflected wavefront is made like this. If this point is Y, at here also Y. Front one is Y. Returning one, front one is also Y, right? At here, we can say inverted reflection, this one, non-inverted reflection. And this is also called rigid reflection. This is called soft reflection. Right, here we have two strings, lighter one and heavier one. Can we copy this one too? Okay. This one is light one, that one here. M is linear density. Can we note it? Linear density of AB smaller than linear density of BC. Okay. This wave pulse transmitted to the point of B. Let's see the point of B. This is rigid one, but this is hard end. Even though it is hard end, it can vibrate. Then this part of this wave will be transmitted like this. Part of energy transmitted. Complete wave, but part of energy transmitted as well. Part of energy of the wave will also be reflected. This amplitude is not fair, right? Like this. Okay, if this point is X, here we have X, here we have X. Then, can we copy the diagram? Here we have light wire, and here we have heavy one. Then, after hitting on here, wave fronts turn back like this. and the other side we can see wave goes like this. Anyhow, amplitude of this one A1, this one A2 should be equal to this one A1 plus A2. අදිද්දි පොඩ්ඩක් උස අඩු වැඩි වුණාට කමන්නේ. If you can indicate this one and this one with the comparison, that's better, right? Okay. Next. This is heavy one. This is light one. But as this one is light one, complete wave will be transmitted right here. It won't be reflected as this is heavy one. Let's see. This is linear density here, mention here. Yes, then this is heavy rope and the other one is lighter rope. Then wave is transmitted only towards that side without changing the amplitude. It goes like this. If this is A, this is also A. Done. Right. Right, copied. Can we see next? $186. Okay, then you are asked to draw when the half of the wave front is reflected from the rigid end, when the half of the wave front is reflected from the soft end, when 1/4 and 3/4 of wave fronts are reflected from the complete theory part, right? Okay, can we complete that page within 5 minutes? Okay, let's start now. Notes පොත් ළඟ තියෙන අය පොත් පෙරලා බලන්න එපා. තනියම ගන්න වැරදුනාට කමන්නේ වැරදුනොත් මෙතනදී හදාගත්ත හැකියි. Okay, let's start now. ඒ අදාළ ටයිම් එකේ try කරන්න. බුදියගෙන ඉන්නේ නැහැ උතෙන්ට වෙලා. Okay, enough time. When half of the wave is reflected, we can show it. Half of the wave is reflected, no? Like this. Half of the wave reflected. Then first half reflected, second half to be hit, no? Then you can see crest, trough, completely opposite direction, same frequency, same wavelength, same amplitude. Then you don't see any kind of wave. Then only resulted one is the string. And if you have drawn a string, then that's perfect. Next one. Here, half of the wavefront is reflected. A rough one is like this. If this is the string, and here we have while loop. When this one comes to here, half is half to be hit, another half reflected. This is soft reflection. This is the reflected one, coincided with each other. This is to be hit. Gap then this one towards right, this one towards left. They are having same amplitude, same frequency, and same all the stuff. Then the string can be seen like this. You can see double wavelength, double amplitude like this across the rod. If this is A, at here you will be see two amplitude, double of the amplitude occurred. Constructive interference. Okay, then 188. Right, when 1/4 of the wave is reflected, 1/4 reflected. This one is this rod. Here we have string. 1/4 reflected. 1/4. Like this, no? This one and this one identical. This and this identical. Then it should be destructive interference. Then we can see the wavefront will be arranged like this. Right here. Wavefront is arranged like this. Okay, next one, 3/4 of wavefront is reflected, right? Reflected 3/4. How? Then this one is the margin. Here we have string. 3/4 is reflected, no? Then to be hit 1/4, reflected 3/4. Lowered, reason, rigid reflection, none, inverting reflection. Then these two will be overlapped. Then you can see that string here, destructive interference, string only seen from here to here. And after that, arranging like this. Cool. Okay, 189. When 1/4 and 3/4 of incident waves are reflected from the smooth end, it's a smooth one. Can we copy like this? Done. 1/4 of the wave reflected. 1/4 reflected. 3/4 to be hit, no? This one to be hit. And another 1/4 reflected. Reflected one like this. Here, crest, crest. Is it like this? This is that half of the wave pulse. This is rest of the half. It's a broken one like that, no? It's like a ripple. Yes. Right here. And this one is this one. 3/4 of wave. 3/4 of wave is reflected. Here we have stream, boundary, 3/4 reflected, then reflected back, and here we have to be hit. Anyhow, same process now, same as this. Right here. Okay. Next one, explain how would you demonstrate the Doppler's effect by using the ripple tank. Demonstration of Doppler's effect by using the ripple tank. Can you explain that? Next page, page number 21. Doppler's effect. To demonstrate the Doppler's effect, we need a moving source, no? It's better to use a vibrating small motor placing on the water surface, and it is traveling from one end to the other end, right? Then wave fronts will be arranged like this, no? Wave fronts will be arranged like this. How? When the source is moving towards right side, towards the moving direction, wave fronts are bunching, no? Closing, yes. Wave fronts are closing like this. Then they are circular wave fronts, right? But here, wave fronts will be closing right here, like this. This is the position of the source. Here we have source travels with a certain velocity towards right side. This is a wave location, here towards location. Now can you explain? How? At this side, wave fronts are closing, then wavelength increases. Wave speed of water surface is written V equal GH root. Balagarin Pasalip. V equal root GH. Then H remains same. H remains same. Depth remains same. So depth is same, then wave speed same. So V equal F lambda we have V same, remain same. Then frequency indirectly proportional to S Darune lambda. Then Lambda shortened, frequency is large. Here we have high frequency. High frequency offered at here, wavelength is large, then low frequency. It is correct, no? Towards the direction of the source. Towards the direction of the source, wavefronts are bunching, then wavelength decreases while increasing the frequency. Then towards the source direction, frequency is high. That is the Doppler's effect. And opposite direction, that means opposed to the moving direction of the source, wavefronts are apart, and then frequency becomes low as the wavelength is large. Okay, right. Copy this diagram. And we have to write the incident, right? Okay. Okay, just write the explanation. Place a rotating motor. Place a rotating motor. Place a rotating motor on the water surface of the ripple tank. Of the ripple tank. It is slowly shifted. It is slowly moved. Slowly moved towards one side. Towards one side of the ripple tank. Of the ripple tank, as shown in the figure. Towards the moving direction, towards the moving direction. Wavefronts are closing. Wavefronts are closing. Wavefronts are closing. Then wavelength decreases. Wavelength decreases. Wavelength decreases by increasing the frequency. This one decreases, right? At this side. By increasing the frequency. Then towards the direction of the source, frequency increases. Then towards the direction of the source, frequency increases. Okay. And away from the source, wavefronts apart. Away from the source, wavefronts are apart. Wavefronts are apart. Then wavelength increases. Wavelength increases by reducing the frequency. By reducing the frequency. By reducing the frequency. Okay, clear. Right. Put up this one, next one, 191 is the question related to the ripple tank, only essay question, right? Okay, can we start now, Buddha? Can we read the question first? What do you call it? Ripple tank is an apparatus used to demonstrate the wave propagation. Underline wave propagation. Wave propagation. And study of wave properties such as, underline, interference and diffraction. The ripple tank, the wave with a circular wave fronts by dipping the vibrating pointer in the wave. A pointer performs circular wave fronts. However, by replacing the point vibrator with a thin vibrating plate with the straight wave fronts can be generated. Clear? We all know that thing, no? Yes. In this case, the motion of the wavefront waves in such that the wavefronts remain parallel to the plate. Wavefronts remain parallel to the plate. We all know that thing, no? Not special one. Next, the speed of wave on the surface depends on the depth of water. Wave, the speed of wave, underline speed, depth. And you are given that one is V equal root GH. And the speed, one can make the part of the tank the shallow by placing the thick glass plate at the bottom of the ripple tank, and its divide in the tank in the region can be considered as different media for the wave propagation. Yes, H is depth of the water, the surface. The speed of water wave is given by V equal root GH, where G is the gravitational acceleration, and the relation applies only when the wave, let's see, the relation applies only when the wavelength of the wave is greater than the depth of water. Wavelength to be very huge, then amplitude negligibly small. That's what, right? And the amplitude of the wave small compared with the depth, as in the case of ripple tank. Those two properties should be managed to apply V equal GH. What are they? First one, wavelength of the wave is greater. Yes. And depth of the wave. Yes, compared with the depth of the wave, the amplitude of the wave is small compared with the depth. Yes. Then next, when the depth is very small, the surface tension effects are significant. When water waves obeys laws of refraction and reflection, deflection similar to the light waves. Underline refraction and reflect. This should be reflection to the right. It's reflection. Okay. Similar to the light waves, this phenomenon may be studied using the Ripple tank. Suppose the straight wave front propagating in the deep region meets the boundary between two regions in such a way that the wave crest parallel to the boundary creates parallel to the boundary. The wave will propagate into the shallow region, region 2, without any change in the direction of the propagation as they enter the shallow region, without any change of the direction, the propagation as they enter to the shallow region. So using the stroboscope. Stroboscope is the item that is used to see the wave fronts without moving here and there, right? The wave fronts are just moving. Then the observation region is also having movable process of the wave fronts. By keeping the stroboscope is the rotating plate with the holes. Looking through the holes, if the hole's frequency is equal to the frequency of the wave propagation, number of waves generated on the water surface as well, the frequency rotated by the stroboscope having the hole, it's like this kind of circular plate disc. It is rotated and it has a certain number of holes. If the frequency of a hole, right, a hole frequency is same as frequency of the wave fronts, then today it apparently seems, the wave fronts remain at rest relative to the water wave. And then stroboscope adjusted to the relevant frequency, yes, relevant frequency, the wave patterns in both regions can be made to appear stationary, yes, simultaneously. Hence, it can be deduced that the frequency of wave in the same in both regions. Frequency, same in both regions, yes. And now you have some questions. Questions, we have to consider number 8, no? Right. Let's take around 6 minutes to complete. Okay, let's start. Quick as possible, you must complete, right? Okay. Can we check the answers for that? බලන්න ලියපුවා හරිද කියලා. Due to phenomena which can be explained by considering wave nature. Only wave nature, right? This is only wave nature. Diffraction and interference only. Diffraction and interference. Roman 2, state the conditions under which the relationship this is valid. Here, we identified this one first. Wavelength of the wave greater than the depth of water, and amplitude of the wave is small compared with the depth in the ripple tank. Can we note this? Right. Next. Roman 3a. If the depth of the region of the ripple tank and 4 centimeter and 1 centimeter respectively, what are the ratio of wavelength? Let's see. V equal GH root and V equal F lambda. GH root equal F lambda. Frequency remains same. It was mentioned in the statement as well. We all know that. You should know it, right? Okay. G common, then lambda directly proportional to root h. Lambda 1 directly proportional to 4 centimeters root. Lambda 2 directly proportional to 1 centimeter root. Dividing each, lambda 1 over lambda 2 is 2. Here lambda 1, here lambda 2. B. The parallel line drawn in the region 1, shown it represent the straight wave fronts in that region. Copy the figure and draw the subsequent wave front in the region 2, indicate lambda 1 and lambda 2 on your diagram. If the angle of incident is 30, find the angle of refraction. Okay, let's see. Motion of the wave fronts. Here, this is deep, shallow region, right? Then it bends towards the normal. So, arrangement of wave fronts. They are closing and bend like this now. Like this. This one lambda 1, this one lambda 2. Right. I, this is R. And you are asked to find angle of incident 30, this one. Then you are asked to find R, no? Okay, then we can write N1 sin I equal N2 sin R sin R, and we have N1 V1 equal N2 V2. Okay, divide each. Then we have n1 cancel. Sin I over V1 equal sin R over V2. So we can say sin 30 over sin R equal V1 over V2. V1 over V2 we identified, no? V1 over V2 same as root of death, like this now, 2. Then can we mention here sin R equal sin 30 divided by 2. Then sin R equals sin 30 half by 2. R becomes sin inverse 1/4. Right, copy the answer. (14° and 30 minutes). Done. Next. The difference between radii between the first and sixth circular crest. First and sixth. 1, 2, 3, 4, 5, 6. We have wavelength 1, 2, 3, 4, 5. Lambda into 5 equal 20 centimeters. Then lambda becomes 4 centimeter. Is it 4 centimeter? Roman 5. And we have to consider Roman 4 too, no? Explain why the frequency of the wave in both the regions is same. Frequency does not depend on the nature of the medium. Yes, write down. Frequency does not depend on the nature of the medium. Frequency does not depend on the nature of the medium. Six. What is the fundamental difference between water waves produced in the ripple tank and sound waves? Ripple tank, water waves in the ripple tank, transverse. Sound waves, longitudinal. Yes, write down. Transverse waves of the water waves. Sound waves are longitudinal waves. Sound waves are longitudinal waves. Done. If you wish to study the total internal reflection of water waves, in which region of the ripple tank, 1 or 2, would you place the source? See, placing the source. This one, deep region, it's rare. This one, shallow region, it's denser. To see the wave, to see the total internal reflection, we have to take the ray diagram like this. This is the intersurface. Here we have normal. This is ray of incident. And then to have the total internal reflection, exactly we have to keep the object in the denser medium. And in light wave should be traveled towards the same medium. This is rarer medium. So we have to keep the object at the medium 2, second medium. Okay, to see the total internal reflection, we have to keep the object at the second medium. Number 2, reason. Explain your answer. To have the total internal reflection, to have the total internal reflection, to have the total internal reflection, the source, the light ray, the right ray, should be traveled from, should be traveled from should be traveled from denser medium to rare medium. Roman 8. Give a suitable label diagram showing the diffraction of water waves in the ripple tank. Diffraction, no? You can draw any kind of diagram, no matter. Diffraction. Wavefronts. Diffraction like this. That's fair, right? Okay. The part of the ripple tank now completed. Right. Let's start the session. Revision number 2, part E, optics, refraction through lenses. Yes, Buddha, right. Let's start, right? Okay. 192. What is mean by focal length of a lens? What is mean by focal length of a lens? Can you remember? Focal length of a lens. Here we have convex lens. This is a convex lens. That. Here we have principal axis. The beam of light fallen parallel to each other like this. And they're converging at a point right here. These light rays are converge at a point on the principal axis. That is called the focus. So, what is the definition of focus? This is the focus. So, what is the definition of focus? The point at which the parallel beam of light is trying to converge at a point after passing through convex lens. Or, as well, right? We have another arrangement. Concave lens, here, this kind of one. Here, principal axis, a beam of light fallen like this. They are diverging. They are diverging from a point on the principal axis, right here. They diverge. Done. This is called the focus. Note down it. Copy both the diagrams. Right. Definition. The point at which the parallel beam of light are converge. Parallel beam of light are converge or apparently diverge. Here exactly converging. Here diverging. No. Diverging from the point on the principal axis. On the principal axis. After passes through the lens. After passing through the lens is called refraction. Is called refraction. Okay, 193. Derive the lens formula by using a simple ray diagram of convex lens. Can we change this one to the convex lens? That's better, right? In the syllabus, we have to demonstrate the lens formula by using convex lens. Okay, let's start now. For the derivation, we have to use the principal axis like this and the plane of the lens right here. And here you are given the lens. Keeping the object at a point right here and formation of image to be considered. This image is formed by this object, by the lens, no? At a point like this. Parallel beam of light forming the images right here, image right here. Let's take with another color. Done. Let the height of the object is h. This is objective distance in between the focal, in between the objective distance and optical center. Here image distance, image height is h dash. Here we have focal length. Done. Okay. Then select these two triangles are similar triangles and these two triangles are similar triangles. Okay, considering similar triangles, we can say H over H dash equate H over H dash equate objective distance U over similar triangles. We write first one. And for similar triangles of this and this is same as this one. H over H dash equal F over V minus F, no? Here, V minus F. This is number 2. Equating first and second. U over V equal F over V minus F. Can I have cross multiplication? VF equal UV minus UF, right? To take a single function, single letter of each function, this whole thing divided by UVF. Can I have here? VF divided by UVF equal UV over UVF minus UF over UVF. VF, VF cancel 1 over U. UV, UV cancel 1 over V. UF, UF cancel 1 over this one, 1 over F here. Here 1 over V, no? Yes. Here 1 over V, 1 over F, 1 over U. Then use the sign convention. Sign convention in practice towards the direction of light rays. Take the minus sign backward from the optical center, backward to the direction of light rays could be positive. So, sign convention 1 over U is plus, 1 over F is minus, minus 1 over V should be minus, no? Then 1 over U equal 1 over F minus, here plus 1 over V. Then we have 1 over V minus 1 over U equal 1 over F. Here we have Lens formula. Done. මෑත විභාගයකදී මේක ඩිරයිව් කරන්න ඇවිල්ලා නැහැ. ඒ අහන අවුරුද්දකදී අහන්න ඉඩ තියෙනවා. Only through lenses. The only lenses we have nearby experience 2011 A level only, right? After that, we had past paper questions related to microscope and telescope. Single lens question we didn't see. Okay. Right. Let's start the question number 194. 194. Complete this one quick as possible. Okay, 194. A needle of length 5 centimeter placed 45 centimeter from a lens. "45 centimeter from a lens," like this. Any kind of lens, right? Can we take like this? This kind of lens. A needle of length 5 centimeter. Pose an image on the screen of 90 centimeter on the other side. Definitely this one, convex one, right? Here we have image at a point of distance, here 90 centimeter. Focal length is not mentioned. This one is 45 centimeter. Okay, objective distance known, image distance known. You are asked to identify the type and the focal length of the lens. It's very easy question. First one, no? Right. Can we manage? 1 over V, 1 over U equal 1 over F. Darwane, objective side is emitting the light rays towards the other side. Then this side is minus sign, this side is plus sign. Okay. 1 over V, 90, minus 1 over U, 45, 1 over F. Common denominator, 90 minus 1 minus 2, right? Equal 1 over F. F becomes 90 over 3, 30 centimeter. Easy. Can we complete now? An object is placed 6 centimeter in front. What is the size of the image? Image height over objective height is image distance over objective distance. It would be 90 over 45, then h dash over 5. H dash becomes 10 centimeter. Twice of now. Magnification doubled, 90, 45. Right. Let's take 195. An object is placed 6 centimeter from the concave lens. Concave, no? 1 over V to be found. 1 over U, 6. 1 over 12. This one plus, this is also plus. Focal length of concave lens is plus. I can verify karan first of all, we have to copy this kind of diagram. This is the objective, 6 centimeter. Focus එක තියෙන්නේ පුතේ දැන් මෙහෙම එන light ray එක diverging at this side. Focus backward positive sign, frontward negative sign. Then find V. 1 over V equal 1 over 12 plus 1 over 6, right? It's 12. 1 plus 2. It's 12 by 3, 4 centimeter. Focal length is image distance, no? Image distance is 4 centimeter. It's a diminished one. 4 වෙලානේ තියෙන්නේ. Right, 196. See the process. (196). A beam of light converges to a point O. A lens is placed in the path of the beam 10 centimeter from O. At what distance from O will the beam converge if the lens A is convex lens of focal length 20 and concave lens of focal length 15 centimeter? Okay. Let's see. A beam of light converge to a point O like this. Beam of light converge to a point O. Right here. Lens is placed in the path of the beam 10 centimeter from O. Like this. Convex lens of the distance 10 centimeter. At what distance from O will the beam converge if the length of the focal length is 20 centimeter? Okay, towards this side, minus signs, towards backward, positive signs. Can we complete quick as possible? Applying the lens formula. 1 over V to be found. 1 over U, 10. Sign is minus. This side equal 1 over 20 minus. 1 over V equal 1 over 20 minus. Minus minus plus taken into the other side. Minus now. Minus minus plus take into the other side. Becomes minus. Common denominator 20. Minus 1 minus 2. 20 over 3 minus centimeters. Then light rays will be converged now. Right here. This point found. Done. 20 by 3, 6 centimeter. 6.67 centimeters. If it is concave lens, repeat the calculation. If it is concave lens, repeat the calculation. Same as that. Beam of light converge to a point right here. Now you are given concave lens is placed to form an image of the focal length 15 centimeter. Yes. To the point of 10 centimeter. Then what will happen? Again, 1 over V to be found. 1 over U, 10. It should be minus equal. Focal length is 15 centimeter. It's plus now. Then 1 over V equal 1 over 15 minus minus plus plus taken into the other side. Minus 1 over 10. Clear? Right. Then common denominator we have 15, 10 now, 30. 30 here 2 minus 3. V becomes 30 centimeter minus. What do you mean minus? Light rays are diverging, but they have converged. Diverging rays are converged on the principal axis right here. Done. 30 centimeter distance. So you can manage this distance is 30 centimeter. It's a magnified one, no? Yes.